In this video, I will talk about dimensional analysis. What is it? And I will mention its importance briefly. To tell you what dimensional analysis is, we must talk about units. If someone has tried to measure your length or did that yourself at one point in your life, then you probably used a large ruler or a measuring tape. You might have measured your length to be 1.53 meters at the time, or 153 centimeters, or 5 feet if you don't use the metric system. Or you might have measured it on a different scale. It doesn't matter. What matters is that in every time you used a device to measure length. We call length a dimension, and I'll tell you why in a bit. There are many scales to measure length, but all scales, like the previously mentioned meters, centimeters, and feet, are just ways of giving length a number, meaning that we are quantifying length. And those scales are called units. Now let's talk about mass. You definitely measured your weight, which is actually mass. There are many ways of giving your mass a number or quantifying mass, like saying you weigh 70 kilograms. Sorry about using the word weigh, I don't make the language. You could also say that you weigh 153 pounds. Sorry again. At the end, mass is a dimension just like length. Time has many ways of quantifying it too. Like length and mass, it is also a dimension. These 3 dimensions, in addition to 4 other dimensions, cannot be written in terms of other dimensions, meaning that they are independent from each other. That's why they are called dimensions. For example, you can't write your length in terms of mass or time. You can't say I'm 2 seconds tall or 2 kilograms tall. You could only say I'm 2 meters tall or 5 feet tall, etc. These 7 dimensions make all the units and their derived units, which are units written as a combination of 2 or more of the 7 basic units that are associated with the 7 dimensions. Don't worry, we will only mention derived units that are a combination of length, mass, and time. Getting back on point, what is dimensional analysis? Well, dimensional analysis is identifying the dimensions that make up a quantity. An example will show dimensional analysis better than a definition. Let's have velocity and find its dimensions. You were taught before that velocity is distance divided by time. Distance is measured in meters or feet or any other unit, which means its dimension is length, and dimension of time is time. So dimensions for velocity is length over time. So you could write it as length multiplied by time to the power of -1. In SI units, it is meter per second. Let's see what the dimensions of acceleration are. Acceleration is velocity divided by time. So it is length time to the power -1 over time. That equals length time to the power of -2, or length per time squared. In SI units, it is meter per second squared. Let's move on to force now. Force is mass multiplied by acceleration. The dimension for mass is, well, mass. And the dimensions for acceleration are length time to the power of -2. So the dimensions of force are mass, length, time to the power -2. In SI units, it is kilogram meter per second squared, which is also the derived unit called Newton. As we said earlier, a derived unit is a combination of 2 or more of the basic units. And as you can see, Newton in basic units is kilogram meter per second squared. What about energy? What are the dimensions of energy? And does it have a derived unit? You should already know what potential energy and kinetic energy are. Let us start by a potential energy of a uniform gravitational field. Potential energy in this case is mass multiplied by acceleration of gravity by height. Mass, well, is mass. Acceleration is length time to the power of -2, and height is length. So the dimensions are mass, length squared, time to the power of -2. How about kinetic energy? Does it have the same dimensions or not? Let's see. Kinetic energy is half multiplied by mass multiplied by velocity squared. There are no dimensions for half. Mass is mass, velocity is length times to the power of minus 1, but remember, the velocity is squared. Then you get mass multiplied by length squared times to the power of minus 2. So the dimensions are mass, length squared times to the power of minus 2. Kinetic energy has the same dimensions as potential energy. So energy, no matter what kind it is, has the same dimensions, always. And they are mass, length squared times to the power of minus 2. In SI units, they are kilogram meter squared per second squared, which is equal to joule. This is our second derived unit, and it is a combination of 3 basic units. Now you can do dimensional analysis of any quantity as long as you know the basic units that make it up.